Chapter 14. But what if things are different? Structures, records, and fields. After having studied and worked with the arrays, you will notice that something is lacking in our exploration of data structures. That is, we do not have any type that can hold mixed types, like something that could hold both an integer and a string at the same time. That is why we introduce the record in this chapter. In this chapter, the limitation of the array. What to do if you must mix data types, definition of the record and its fields, the struct, short for structure, programming with structure and records. What can you do now? One step further, arrays of records and structures. Beyond the array, the record. Once you have seen the standard data types, integer, real, character, string, and boolean, you are ready to design your own data types. This includes the array, whereby you can declare a collection of one type. Now we can introduce the record, which allows you to create a collection of different types. The record is used to hold various data. If you want to keep track of information about an individual, such as her name, age, and grade point average, GPA, a record would be a good choice to hold this data. The name would be a string, the age, an integer, and the GPA, a real number because of the decimal. Think of the record as a box into which you throw different things. Unlike the bureau analogy used for the array in Chapter 9, where you only put clothing items into the bureau, the box and an analogy we use for the record can hold anything that we define for it. How to design a record. The first thing to consider about a record is what types of data you would like to put inside of it. In our previous example, we grouped together a string, an integer, and a real number for a record that keeps information about an individual, probably a student. Let's give names to each of these types. String, name, int, age. Double GPA. Recall that variable names do not have any periods in them. You will soon see why. The preceding declaration shows each of these variables declared separately. The purpose of the record, however, is to group these variables together into one new variable of the record type. Defining a record. Before you define a record, you need to think of a good name for the record's contents. Let's name our record individual for the information we just mentioned. The syntax for declaring a record will include braces to show where the record begins and ends. Here is an example of a declaration in the programming language C++. A record in C++ is called a struct, short for structure. which suggests that you are building something, in this case, something unique. Struct individual, opening brace, empty spaces. The different data types go in here, closing brace. The semicolon ends the declaration. This is just a skeleton of a definition. We have not finished it yet. Inside the braces, we will declare the internal variables of the record, each of which is called a field of the struct record. Struct individual, opening brace. String name, int age, double GPA. The different data types go in here, closing brace. The semicolon ends the declaration. Individual is the name of a box with 3 things inside of it: an individual's name, age, and GPA. See figure 14.1. Figure 14.1. A box is shown with the name individual on the outside. Inside it are the name, age, and GPA fields. Reserved words. Reserved words in any language, sometimes called keywords, are words set aside because they have special meanings in the language. When the compiler or interpreter encounters a reserved word, it will translate it according to the meaning already associated with that. Let's consider this brief list of reserved words that would be common to most programming languages: for, do, while, and all. Because these words have been reserved, a programmer will avoid using them as a choice for a variable name. Now that you have the skills to create your own variable types, as well as names, it is important that you understand that you cannot use these words for variable names in your programs. The compiler, when it encounters a reserved word, will start to execute the command or commands associated with that word. If the compiler sees the word for, it will assume that there is a loop that must be executed. This is just one example, and it is the main reason why you cannot choose a reserved word as either a variable type or variable name. Declaring one or more records. Once you have defined the record, you are ready to declare one or more records. When you declare a record, you will be telling the compiler that a variable of type individual now exists. Remember, because of the declaration you made to the compiler, a new type, individual, now exists for the duration of that program. This is in addition to the standard types: int, char, double, and so on. Let's declare 2 variables of type individual. Individual, first person, second person. Individual is not bold-faced because we want to emphasize that it is not a reserved word. Once you have declared these 2 new variables, the compiler will set aside the memory for each variable, which includes memory for each of its fields. The name you give that individual is that variable name. distinguishing among the record's type, the record variable, and the fields. The most difficult part of dealing with records called structs in C++ is the confusion that arises from all the variable names that are part of the definition. Let's take a moment to clarify what each variable name, struct, record, name, and type refers to. When a record is defined, the compiler is informed what it will contain, and as a result, sets aside the appropriate memory for everything that it contains. Each internal variable, each field, has its own type and memory requirements. Each record has to be given a name to identify it as a new type. That way, a later declaration of the type is possible. Let's examine two different type records with similarities. A struct that contains two strings and one character will be used to define a person's name, middle initial, and last name. That struct will be given the name identity. Identity represents a new type. Recall that C++ is a case-sensitive language, so identity must begin with a small letter even when it appears as the beginning of a sentence. Struct indicates a new type. Type name, like int, char, etc. Struct identity, struct definition begins here. Opening brace, string, first name, arrow upward, field type, arrow upward, field variable name, string, last name, upward arrow, field type, field variable name, character, char rather, mid initial, init, up arrow, field type, field variable name, closing brace. Another struct will be defined with an integer and two strings. The integer for the apartment number and the strings for the street address and city. We assume all these locations are for people who live in apartments. This struct represents a new type called location. For the duration of the program, we have 7 types available: an int, string, double, char, boolean, identity, or location. Struct, location, opening brace, int apt, no. String, street, string, city, closing brace. Defining a struct in C++ allows us to create a new type. This struct is really just a collection of variables, usually grouped together for clarity in the design of a program. In the identity type, 2 strings and a char are used to represent the full name of a person. The location type has an integer and 2 strings to represent a complete address. When you declare variables of these types, you declare them in the same manner that you declare any variables. You state the type first, followed by the variable name. Let's declare some variables of type identity and location. Identity, first individ, second individ. Location, address 1, address 2. So 4 variables have just been declared, and all of them are as yet unassigned. These variables would be declared alongside other variables used in the program, as in this example. Int x char initial identity, first individ, second individ, location address 1, address 2. How to assign record variables. When you assign any record variable, you need to assign each field of the record. The record is, essentially, a group of other variables of the fields. When you assign a record or struct, you are really assigning its fields. It is important both to recognize the field's name and to distinguish it from the field type. In order to assign a record, we focus on the field name in the assignment statement. Consider this example where we partially assign 3 fields from an identity type. First name equals Mike, last name equals Smith, mid-init equals T. In order to complete the assignment statement, we need to use the variable name of the identity type. In that way, we will be communicating to the compiler that we understand the connection between the field name and the new type. First, we need to examine the meaning of a delimiter, which will allow us to make this connection for the compiler. Using a delimiter, we will access the field names through the variable names. Using a delimiter. A delimiter is a punctuation symbol used to get access to an internal part of a larger part. In the case of a record or struct, the record or struct is the larger part, and the field is the smaller part. The delimiter is used to connect the variable name to the field name. When you want to access the fields, you use the variable name that was declared, followed by a delimiter and then the field name. You can use this sequence in an assignment statement or any other acceptable statement for the variable. Let's look at an example using the variable name, first individual, and one of its fields, first name. We will use the period delimiter between the variable name, the name used for the new type, and the field name. First individ, first name, variable name, field name. Notice that we have not used the type names in this example. Type names are only used for declarations and definitions. Consider the next example, which is a complete assignment statement. First individual, first name equals Mike. Variable name, field name, assigned value. In this example, we are really assigning the field of the variable. When all the fields of the record have been assigned, then the record is considered assigned or loaded, as I like to say. Let's assign the other fields of this struct. First individ dot last name equals Smith. First individ dot mid init equals T. Note: Periods are often used to separate larger parts from smaller parts. Just consider this fictitious internet address, www.mycompany.com. Notice how the period is used to separate the company name My Company. Notice how the period is used to separate the company name My Company from the com or the entire commercial group of companies on the web. Letting the user assign a record. The user can assign a struct by responding to the CIN statement. We will follow the syntax used in the previous examples. Instead of using an assignment statement with the equals sign operator, we will use the CIN statement. The user should be given some prompt so that she understands what input she should be typing. Here are some examples using the variable name address1 followed by all the field names in the location type. Cout. Please type the street address and L. Cin. address1.sstreet. Cout. Please type the city endline. Cin. address1.city. Cout. Please type the apartment number and L. Cin. address1.state. Now the record address1 has been completely assigned because all of its fields were assigned. Remember that when you declared address1, it acquires all the field names and types associated with the new location type. The same thing can be done for address2. Either the user or the programmer can assign it. Right now, only first individual and address1 have been assigned. The other two record variables, second individ and address2, are unassigned. See figure 14.2. Figure 14.2. A diagram of the four record variables is shown. Either the fields have been assigned or they have been left blank to show they have no values yet. Top left box. First individ. Mike, first name. Smith, last name. T, middle init. Second individual. Top right. First name, last name, middle initial. All fields are blank. Address1, bottom left. 3, apartment number, 140 Main Street, Maple Street, Clareville, City. Bottom right, address 2, apartment number, street, city, all blank. Examples of different records. Records are very useful for storing information about items with varied data. Think of the inventory of a store. Think of the inventory in a store for each item sold. A piece of clothing, for example, could have the following fields to describe it. Struct item, opening brace, string, item type, pants, shorts, shoes, etc. Int floor where item is found. Double price, the price of the item. Int percentage, highest percentage discount allowed on item, closing brace. An item could be a pair of jeans, found on level 2 of the store and priced at $48, but with an allowable discount of up to, but not higher than, 50%. Another example is a struct which contains information about a CD in a music store. Struct CD, opening brace, string name, the name of the CD, string artist, the artist's name, double price of CD, int year released, year CD came out, closing brace. An array of records. Usually, when we define a record, we need it because we are anticipating a program which requires variables for lots of data. Think about the problem of storing all the pertinent information in a collection of CDs, books, or DVDs. You are not really designing a record data structure because you have only one CD in mind. You are really contemplating storing the data for all of your CDs. What we need to define is an array of records where each member of the array is a record. See Figure 14.3. Figure 14.3. An array of records is shown where each slot of the array is a record. First CD, second CD, third CD, fourth CD, and fifth CD all have name, artist, price, year released. Defining an array of records. We define an array of records just as we would define any array. But first, let's review a definition of that we saw previously, the definition of a CD. Let's start by restating that definition, which was a struct. Struct CD, opening brace, string name, the name of the CD, string artist, the artist's name, double price of CD, init year released, year CD came out, closing brace. Next we will declare an array of CDs. The first step is to state the type, CD, followed by the name we wish to give the array, followed by brackets with the number of array members inside. Remember that the array declaration is like any other declaration, except that the brackets are used with the numbers of intended members inside. CD, type, my collection, array name, 25, number of members. Each member of the group is a CD struct. Look at this list of variable names on the left and the types on the right. Variable name, type, my collection, 0, my collection 1, 2, and 3 are all CDs by type. Caution. Always define a record struct before declaring an array of that type. Otherwise, the compiler will not understand what the array contains. Where to place the record definition. You need to precede the array declaration by the record struct definition. Otherwise, the compiler will not understand what you are declaring. Since our example has been written in C++, we will refer to our record as a struct. Recall that you are creating a new type when you define a struct. If you think that you will be writing functions that use the struct definition, You will need to put the definition in a place where everyone can recognize it. For this reason, we place the struct definition at the top of the program. Consider the following skeleton of a program. Notice that we have placed the struct definition at the top of the program, above the function headings and the main function. # include iostring.h, # include string.h. Struct book, opening brace, string title, string author, int year, char discount, closing brace. Void print or book B, void change discount book B, int main, opening brace, declaring three variables of the book type: book, my book, your book, x, ... return 0, closing brace. The book's definition is placed above every other part of the program where a variable could be declared. The reason for placing it here, as opposed to placing it just before the declaration, is to allow all functions, including the main function, to recognize this new variable we have just created. Our next topic concerns the scope of a variable, and scope will help you to understand the placement of the definition. Every part of the program should recognize the struct definition of a book. For this reason, we place the struct definition above all functions. By placing the definition here, we are making the struct definition global, that is, the definition is recognized globally or everywhere within the program. Global variables, local variables, and their scope. There are other ways to classify variables other than what type they are. Variables can be classified according to the extent of their recognition. If the variable is recognized by every function, including the main function, then we say it is a global variable. Think of some of the most popular actors, rock stars, and politicians. Some are recognized only locally, while others are recognized everywhere or globally. Think of the example of a U.S. senator. She might not be widely recognized outside of her own state. Now take the majority of the Senate. Many people would recognize him because... Now take the majority leader of the U.S. Senate. Many people would recognize him because his popularity would extend farther than the state that elected him. However, he would probably not be recognized outside of the United States. Next, consider the example of the President of the United States. Most people would recognize the name of the President of the United States. Each of these individuals has a scope of recognition. The term scope refers to the largest possible place where that individual is known. We use the term local to describe a limited scope, one that is not global. Individual, recognized when, scope. A U.S. Senator, the state that elected him, local to the state. The leader of the Senate, most all states, local to the U.S. The president, most all countries, global. Another example to consider is the scope of recognition for 3 soccer players. The first player is the best player in your town soccer league. Let's call him Joseph Thomas. Most people in the town recognize Joe because they have been watching him play since he was a child, and they know how good he is. He is recognized throughout the town, but relatively unknown beyond there. Now take a well-known college player. He plays on a college team and is so skilled that most college players have heard of him. His scope would be the college teams, including the players and those who watch their games. Now take Mia Hamm. She has played in the Olympics, the World Cup, and professionally. Many people in many countries have seen her play and have heard of her. Her scope is much larger than the college player or the town player. We would consider it global. Individual, recognized where? Scope. Town player, the town, local to the town. College player, the college circuit, local in the college circuit. Mia Hamm, the world, global. Now consider a variable's scope. If a variable is defined within a function, it is a local variable, because it will only be recognized within that function. A variable's scope refers to the largest possible area of recognition. For local variables, the scope is usually the function where it was defined. If a variable is recognized everywhere, we call it a global variable. All functions recognize a global variable. A global variable must be defined at the top of a program, outside and above all the functions, including the main function. In our example, using the struct, we put the definition of the struct before all the function headings and so forth, to ensure that it would be a global variable. We would also say that its scope extent of recognition is global because it extends through the entire program. # include iostream.h, # include string.h. Int x, a global variable. Struct book, a global structure, another global variable. Opening brace, string title, string author, int year, char discount, closing brace. Notice the variable x. It is also a global variable. All functions will recognize x because it has been defined above everything. All functions that follow can now use the book type. We do not need to redefine it inside of every function that would want to use a book type variable. Note, using the same name for a variable in different functions is okay, because these functions are separate, and so there will be no confusion for this compiler. In more elaborate programs where functions call back and forth to one another, this may not be the case. Caution. Global variables, although useful, can pose problems for programmers because all functions have access to the global variable at any time. Sometimes the values in a global variable will be inadvertently changed, and this may not be what the programmer intended. Summary. We introduced the record, which is a data type designed to hold different data types. Each type within a record is called a field of the record. In C++, a record is known as a struct. When a struct is defined, it is given a name. This name refers to the new type of variable that has just been created. Records can be assigned values just like any variable. To assign values to a struct, we assign each of the fields of the struct using the field names. We introduced an array of structs. This is very useful since we frequently need to hold data for several structs, not just one. Next, the scope of a variable was introduced. The scope represents the extent to which a variable is recognized in a program. If a variable is recognized everywhere in a program, we say that the variable is global. If it has a limited scope, then the variable is local. Variables defined at the top of a program are global, since all functions, including the main function, can recognize them.